So here I have a sphere or a globe that I can rotate freely forward, that is west to east, or backward, that is east to west. Somewhat similar to the eChalk model that you're using, but I have more control over it. But anyway, as you can see, as I'm rotating this globe, the background stays still. So it's in fact a sphere in a still sky. I can of course change my view here, and then the background moves. But if I just rotate the sphere, then the background is still and only the sphere is rotating. And by the way, there's Orion, Betelgeuse, Aldebaran, Sirius, and where is it? There's Polaris over there. But you can't, of course, in this view tell where the hell over the globe they're located. Now on this globe here I have 4 cameras attached, looking north, east, let me disable this widget here, east, south and west. Now as I rotate the globe, the cameras move with the globe, so they stay on the surface. Okay? And actually this is a full-on observer. You'll see later I can change its position. I can input the latitude and longitude and it'll move. But anyway, right now it's located on the equator and it has 4 views looking directly north, south, east and west. Okay? So I'm now gonna minimize this view like this. So here's that view. And here I have the 4 views from these cameras. From the north facing one, here you can see I can rotate it and you can see its view moving in here where my mouse is and there in that small sphere view. Okay, this is not north facing. Okay, this is south facing. Okay, so north and south. And similarly this one is east facing, as you can see there on the sphere view. And this one is west facing. Okay? And I can easily set their altitude exactly. I mean where they point in the sky exactly. Here, this rotation, I can just turn them to whatever altitude I like, precisely. Okay? Right now they are all leveled. They're exactly zeroed out, so they point at the horizon, all 4 of them, just in different directions. Okay? Now let's see what happens when I start rotating the Earth. As you can see, I can do this, just change this angle. I can do it by small increments, or I can just start dragging here. And watch what happens in the views when I start rotating the Earth. Do you see what happens? Do you see how the north-facing camera sees the rotation of the stars and the south-facing camera? And you can see that in the north they rotate counterclockwise and in the south they rotate clockwise. Okay, and the eastward camera, as you can see, the stars move from bottom to up. They raise from the horizon. And the opposite is happening in the western facing camera. The stars move down. That is exactly what's happening in reality as well. When you go out and start filming the stars on the equator. And by the way, there, see this little star here that just appeared on the horizon? That is Polaris, because you can actually see Polaris on the equator. Because it's not exactly over the pole, it's actually what, 3/4 of a degree off the pole. So it does pop up from the horizon on the equator. But that also means that right now this north-facing camera is looking directly parallel to the Earth's axis of rotation. Okay, I'm not looking straight on the celestial pole. You're right at that. I'm not. I'm looking a very tiny fraction of a degree off of it. But it's so small that at this scale it just isn't noticeable. and it isn't noticeable in real life as well, because the radius of the Earth compared to the distance to Polaris, for example, it's basically zero. It's so small a number you just wouldn't notice the difference. Okay, but anyway, let's move on. Neither of us probably has ever been on the equator. Well, maybe you have, I don't know. But the thing is, I can grab this chords here and start moving my observer south or north. Let's say I'll move him north to your latitude. Oklahoma is about, what, 35 degrees? And I can just type in the number here. You see, I can type in 35, and you can see that the observer jumped north. But I want to do it gradually. I want you to look what happens when I move the observer gradually. Watch at all the four views. Remember, north, south, east and west. Okay? Watch what happens, and then rewind the video and watch again on different views if you can't catch all four together. I'm gonna move him slowly to 35 degrees north. Okay? Moving and moving and moving and moving and moving and moving. I'm gonna stop right now. You can see how in the north view the stars now move up, in the south view the stars now move down, and in the east view the stars rotate clockwise, and in the west view counterclockwise. And I'm still moving and 33, 4, there, 35 degrees north. Okay, the reason why these views behaved like that is it's because the movement north is in fact just rotation around the Earth's center by 35 degrees. So in fact the north and south views behaved like normally the east and west views do, because I was rotating around different axes. But anyway, I moved 35 degrees north, and you saw that the stars in the north view moved up. By what amount they did move up, Chris? How do you think? Well, I can tell you exactly by which amount. By the same amount that I moved north. And I can in fact just copy, here I moved actually 35.3 hundredths of a degree. I can just copy this latitude value right here, grab my north facing camera and input the same value for its rotation above the horizon, and bam, the camera is now again pointing directly at this star, Polaris, because as I moved 35 degrees north, it moved 35 degrees up. And I can easily check it. I can now again rotate the Earth, and you can see that the Polaris is staying near the center of my frame and all the stars rotate around it, just like they would at your in Oklahoma, at your location, because this is the same latitude. You go out, you look north, you raise your camera 35 degrees, you see Polaris, and the stars will go around it. And let's just even set the coordinates to be in Oklahoma. Let's just first rotate the Earth so that we can see the US better, like maybe from this angle. Okay, and now I'm gonna grab the coordinates and move the observer west to minus 97 degrees. And there, 97.3, okay. Good enough. I think it should be close enough to Oklahoma anyway. Okay, and still, the cameras are still pointing north, east, south and west. I just moved the observer himself. Okay, and this one, the north facing camera, is still pointing at Polaris. And as I rotate the Earth, you can see how the stars, all the stars move in a circle around the Polaris, around the center of my frame. It's very, very possible on a sphere. It's because this is what actually happens in real life, Chris. Furthermore, I can take this south-facing camera and point it to 90 minus 35, 90 minus the latitude. And now it's pointing directly at the celestial equator. These are all very easy numbers to remember because you just take your latitude, and from it you can tell everything. And now as I rotate, you can see that the north-facing camera here, the rotation is still circular counterclockwise around the center, but here the stars just move from left to right because this camera is looking at the celestial equator. It's always very easy to tell what you should be able to see in the sky, which direction the stars will be moving and whether they should rotate or not, because it's so simple on a sphere. You just need to know the latitude and the angle, the altitude in the sky, and that's it. Everything else follows from that, Chris. It works precisely on a sphere. In fact, also, why do you even think that your latitude matches the altitude of Polaris in the sky? Well, if I set my latitude to 90 degrees, there, so the observer is all the way here on the North Pole, then the Polaris should be all the way over my head, so I should be looking up 90 degrees. Okay, there's Polaris in the middle of my frame. But if I take the observer and move him to, say, 80 degrees latitude, so 10 degrees south, okay, as I move him 10 degrees south, his up direction also moves 10 degrees, and so he now needs to adjust his view to look at Polaris by 10 degrees, so 90 minus 10. You see? And if I move another 10 degrees south to 70, I need to again adjust my view by 10 degrees, so I need to look 70 degrees up to keep looking at Polaris. That's what's going on here. As you change your latitude, you move on the surface of a sphere. You rotate around the center of a sphere, and so does your view rotate with you. And that is why to keep looking at Polaris, you need to keep changing it. You need to keep matching your view to your latitude. It's that simple. And still, even here at 70, what was it, 70? Yes, at 70 degrees, if I'm standing at 70 degrees latitude and look 70 degrees up in the sky to the north, I'll still see the rotation of stars around Polaris. And now, of course, with this south-facing camera, I no longer see the horizontal motion because I'm no longer looking directly at the celestial equator. Okay. And watch what. Let's return for a second to that North Pole here. Set the latitude to 90 degrees. I'm here at the North Pole. If I level out all my cameras, if I level the north-facing one and the south-facing one, here 0 and 0, then in fact all 4 of my cameras are right now looking at the celestial equator, and if I rotate the Earth, I should see the horizontal motion. It's that simple, Chris. There's no magic behind it. It works on a sphere. The fact that you don't understand why it works on a sphere does not invalidate it. Take care.